So, welcome all of you. In the last 1 or 2 classes, we have been discussing more about heteronuclear correlation experiments. Extensively we discuss direct correlation experiment, inverse correlation experiment like HSQC, and how we do the experiment, how the pulse sequence we understood, where we transfer the magnetization from proton to carbon, take back carbon to proton. Of course, I took the example of carbon. It could be any dilute spin to any abundant spin, doesn't matter, any of the 2 abundant dilute spin you can consider for HSQC experiment. And of course, we also understood how to interpret the HSQC experiment. Varieties of experiments are possible, proton coupled, proton decoupled in either dimensions. We took the example of how to interpret the coupled decoupled HSQC spectrum, some hypothetical molecule where we could get 1 bond CH couplings and also long range proton-proton couplings also possible. So, we could get like analogous to the, if you take the coupled spectrum, like in the proton spectrum you have carbon 13 spectrum, proton carbon 13 satellites. From the satellite spectrum you get HH coupling. Identically in the direct dimension, the proton dimension, you get proton chemical shifts plus 1 bond CH and also HH couplings. That was the coupled HSQC. In the decoupled version, CH coupling will remove and we get only HH couplings. So, many such examples are available to interpret the spectrum, and that we took a few examples to say how we can interpret a realistic example of the molecules. But of course, in a crowded region, what we can do is we can identify CH carbon, CH2 carbon and CH3 carbons based on the number of protons attached to carbon. How we do that? In the carbon 13 NMR, when we understood, we also discussed about depth sequences, depth 45, depth 98, depth 135 are the 3 experiments used to identify different carbons, like carbon 13 editing we can do to identify different carbons. Depth 135 sequence, if you join for this HSQC, that is called multiplicity edited HSQC, wherein you can identify all CH2 carbons attached to 2 protons, that is even number of protons, they become negative in intensity, whereas CH and CH3 carbons are positive in intensity. So, that we could find out from the looking at this sign, and we also got the cross section to see they are really negative in peaks in the intensity portion and then positive for CH and CH3. And of course, the example of the 3-heptanon, methylheptanon and ethyl acetate we took to see how we can interpret the HSQC spectrum. So, we will continue with from that now with another example, 1 or 2 examples, a few more examples, and then we will see what are the other things we can do and few more details about HSQC we will try to understand. Of course, this we started also, I discussed this. This is the molecule which we analyze in the proton spectrum. In the phenyl ring, this will give only 2 protons are there, which are 2 carbons attached to 2 protons. They are from the proton spectrum which you analyze, these are the 2 protons, and the carbon chemical shifts we can get, and then if you from this, and then of course from this you get carbon chemical shifts and proton chemicals we get like this. Of course, for the other phenyl group there are 4 protons and I wrote already 2 of them. This we have analyzed. Once you know the analysis of the proton spectrum of the molecule containing phenyl groups, and using that you can also assign HSQC spectrum and get carbon 13 satellites. But only thing you should see here in this molecule, there are the different carbon 1, 2, 3 and 4 carbons which cannot give rise to any peaks in the HSQC, because HSQC is only for directly bonded carbon proton, 1 bond JC should be there. But how do you make sure, how do you assign this type of carbons? That is the thing which we are going to discuss today after a couple of slides. We will continue further. We also discuss alpha and beta glucose, mixture of 2 glucose are there. In the D glucose we have alpha isomer and beta isomer in the ratio of 34 into 60, 36 into 64, 34 into 66 with the ratio that we saw that. And of course, multiplicity edited we can see here, we can get these are all red which are CH2s, rest are all CHs, we can easily identify by doing this. And of course, anomeric protons we all know, these are the 2 things which we use this start the analysis of the Cauchy spectrum also. So, starting with this, of course, this is the anomeric proton beta for the beta glucose, and of course, this is the carbon chemical shift and this is the proton chemical shifts. Similarly, for anomeric proton of alpha, and the expanded region of this one is taken here. When you expand that, basically what you should understand is proton 6 in this has CH2s, that is what we see red color here, even number of carbon. But you see, interesting thing is these two protons are non-equivalent. They are non-equivalent protons. Although carbon chemicals, they attach a single carbon. So if you see that, very easily you can identify. In fact, if you get a difficulty of which proton, whether 6A or 6B or whether it is alpha proton or alpha isomer or beta isomer, you can identify here. Simply go horizontal along this axis. Okay, this corresponds to alpha isomer, and there are two protons here. This is the carbon 13 chemical shift. These are two proton chemical shifts from the center. If in the crowded region, just from the center we can identify the chemical shift here also. So there is no confusion at all. Here also, if you see, this is a carbon chemical shift. Exactly from the center you get proton chemical shift for both alpha, 6A and 6B of the beta isomer. This is the advantage. Same carbon, two different protons are attached, but non-equivalent to different chemical shifts that easily you can assign by using HSQC like this. This is an advantage of that. Of course, same thing when you expand it, you can clearly see for the alpha, for the proton 4, again alpha beta, when there is a crowded region, very easily you can identify which is which. Okay, this is the extension of those things for alpha and beta isomers. All of them very easily you can start doing that. This is the beta isomer, proton 2. This is carbon 13. Similarly, this is for 5, this is 2, alpha, all beta and alpha carbons. Protons we can get chemical shift also. Of course, from HSQC also you can get proton chemical shift. Since you already analyzed the Cauchy spectrum, very easily we can go and continue with this thing. Okay. With this, of course, HSQC spectrum is fairly easy to interpret like Hetcar experiment. There is no difference at all. One thing we may have to answer the question. In a molecule, you have long range couplings. 2 bond CH, 3 bond CH also is there. But we observe only 1 bond correlation in HSQC, 1JCH correlation. The question comes, why 2JCH and 3JCH correlation peaks, cross peaks are absent in HSQC? If you have to answer that, first of all, we have to find out the cross peak intensity. I don't have to go into the mathematics of that and discuss everything. It is all very lengthy mathematics. One can find out what is the cross peak intensity. The cross peak intensity is simply given by an expression like this: alpha into sin squared pi by 2 star into J observed or J filtered. What is J observed is the actual JCH value. J filtered is the value used for calculation of the mixing time. What is J filtered here? In our case, J filter is 1 bond is 1JCH. Observed is usual. Okay. So for JC filter is set for using 1JCH as 135. But in the long range coupling, if I have to see in the what is JCH, long range coupling is of the order of 5 to 10 hertz. Sometimes 2 bond, 3 bond if you want to see. Let's say 4 hertz or 5 hertz will be there. What is the intensity of the cross peak of when the long range coupling is of the order of 4 hertz? Just plug this value into this equation. There is not a big mathematics. We have sin square pi by 2. J observed is the value which we are looking for. We are observing long range coupling. And this is the filter we have set for 1J, 135 hertz. That is some value I have chosen. It can be anything. Approximately around 140 to 150 hertz is what is normally chosen. Let us calculate the intensity of the cross peak due to long range coupling. First, J filter I use 135. J observed I use 4 hertz. I have plugged in the value. Sin squared pi by 2 into 4 divided by 135. This is the equation. See equation here, J observed or J filtered. So observed is 4 hertz. I want to see why I am not seeing the cross peak if there is a long range coupling of 4 hertz in HSQC spectrum. 1JCH is 135. Just use simple calculator. Calculate this value. Calculate what is this value of sin squared for this particular value. This value you can find out, it is 2.6666 and sin squared value of that is 0.0022. What does it mean? The cross peak intensity is 0.0022 percentage with respect to JCH, one by the filter what you have used. That is, it is 0.2% intensity. If JCH peak is 1 bond coupling is of some intensity 1, let us say, Compared to that, the relative intensity of the observed peak for long range of 4 Hz is 0.2%. Hardly you can see that. That is the reason you will not be able to see that. You understand why one band coupling only are seen in HSQC. Why we are not seeing the long range coupling is because of this. Intensity, if you calculate for 4 Hz, it turns out to be 0.2%. Okay, you may say 4 Hz, why it is not a realistic value. Let us take some other value, 8 or 10 Hz, 15 Hz. Doesn't matter. We will see 8 Hz. Let us see it double the long range coupling. Instead of 4 Hz, I look for peak which is 8 Hz. Why I don't see that? We will plug in this value, sin squared pi by 2 star 8 over 135, and this is 5.333, and sin squared of that is 0.0084. What does it mean? Intensity is 0.86%. Even then you don't see. You are looking at carbon 13, remember. HSQC, we are seeing carbon 13 long range correlation. So, with proton, and this is such a small intensity, the cross peak compared to the cross peak you get for 1JCH set of 135 Hz, you will not see that. If cross peak for 1JCH is this size of this value in the area and other one is this much. So, relatively it is so weak you do not see it. That is the reason why long range couplings are not seen in the HSQC experiment. Okay. So, the cross peaks are too difficult, usually not seen because of this very low intensity. Of course, in some example I want to warn you, you can get long range JCHR also, they are quite large, because JCH in this molecule like this, for example in a phenyl group with C double bond CH, you know 2JCH here is nearly 50 Hz. It is not 8 Hz. Now plug in this value here, and for in this molecule, this carbon to this proton coupling is about 26 Hz. That is too large. See 49.5, almost more than 1/3 of 135 Hz. As a consequence, they will give rise to peaks. In such examples, long range correlations are also seen HSQC, but with weak intensity. You can calculate what should be the intensity of that peak compared to 1JCH. It is reasonable value intensity in this case compared to previous example. So, these are all specific examples. You may get long range correlations also. One may ask a question, am I doing HSQC only for carbon 13? No. Most of the time biomolecule people, when they study proteins, peptides, etc., they have molecules like this. For example, in the case of a tetrapeptide, we have NH. I told you these correlations, each amino acid has an NH group, we can get the nitrogen 15 proton HSQC. Then you can identify chemical shift of the nitrogen you get and correlate those NH peaks to corresponding proton chemical shift. And if you have a bigger molecule like protein, there is n number of protons, huge complex HSQC spectrum you are going to get, and we can start interpreting each of them. And this is a simple example of this case. We are going to see 3 peaks are here and 3 NH peaks we are going to see here. Okay. Okay, this NH2 is there, this 3 NHs are there, and of course this is also there one more, but we are seeing, of course this may be overlapped here. These are 3 doublets, these 2 doublets are overlapped here. Okay, and if you take the projection of that, you will see that. And this is the projection of HSQC for the previous molecule. The spectrum was obtained in just 1 hour. Remember, just 1 hour, and we are going to get the signal. The same spectrum without HSQC, conventional way, for 15 hours, no signal, nothing is seen, because nitrogen 15 is inherently very low sensitive, very insensitive nuclei. So, you see, you are not seeing any peak at all. This is the advantage of HSQC. So, HSQC, what I want to summarize here is, you are not only seeing carbon 13 proton HSQC, you can get nitrogen 15 proton HSQC also, and especially in the biomolecules like peptides and proteins, nitrogen 15 HSQC is routinely used, and you can see a reasonable intensity of the peaks in the cross peak. And if you take the projection, we will see very good peaks with very good signal-to-noise ratio compared to the direct observation of nitrogen 15. So, this is what I just wanted to tell you about nitrogen 15, carbon 13 proton, nitrogen 15 HSQC. You can take any other heteronuclei also, no problem. So, basically we understood how do you interpret the HSQC spectrum, why we do not see the cross peak in HSQC, especially due to long range carbon proton or nitrogen proton couplings. So we understood that and took a lot of examples to interpret everything. And we need to understand another experiment called HMBC, heteronuclear multiple bond correlation. Multiple bond means not several at a time. Two nuclei separated by multiple bonds. That is what the convention meaning. So multiple bond correlation, we can use that. Advantage here is it is not only directly bonded, long range coupling. It's remotely bonded. That we can get. This is the very immediate advantages. For example, directly one bonded carbon proton can be seen, but there is a, let us say, O here in between. This 1, 2, 3 bonds separated, 3JCH is there, reasonable. We can see that. And of course, there is a carbonyl carbon which is 2 bonds separated and coupled to another proton somewhere, let us say. Can we see? There are long range couplings very well known in the carbon 13 NMR. We can observe long range CH coupling. These are all reasonable value. Okay. And then how do you detect such carbons? First of all, the advantage of that is non-protonated carbon which you don't see in HSQC can also be utilized because of the long range coupling to different protons. So salient points of HMBC, what do we do when we want to do HMBC? First of all, HMBC is usually acquired in magnitude mode. HSQC, as I said, is always acquired in phase sensitive mode. Very easy. And of course, HMBC, because a magnitude mode node means real and imaginary will take some of the squares of these two and the square of that and get the intensity. And no question of phase correction at all. In the HMBC spectra, there is no need to do the phase correction because always it is recorded in the magnitude mode. This is one thing. Secondly, usually HMBC is acquired without decoupling. There is no need to do the decoupling here because long range coupling is there, which is very weak. And of course, there is no advantage of this. There is no restriction the acquisition time. You can acquire for a long time. That is an advantage. So it is always recorded without of course, you can do the decoupling. There is nothing. Nobody can stop you. But generally, it is without decoupling. And here, cross peaks are always split into doublets in the F2 dimension. Why? We are not doing decoupling. There is a long range 1J, 2J, 3J. CH couplings will be there, which is of the order of 8 to 10 hertz. So it will be seen. Sometimes what happens, long range coupling is very weak, you will broaden the signal. And for example, when a peak is a triplet in 1D NMR, the cross peaks appear as doublets of triplets. Because 1J coupling is here, cross peak, and in the 1H NMR it is a triplet, and the cross peak will be triplet like this, doublets of a triplet. And another thing is, remember HMBC is very, very less sensitive than HSQC. Why? Very easy, you can understand. Remember in the long range, I told you even during the TOXI polarization transfer, when I told you the polarization transfer efficiency is better if the coupling strength is larger. If the coupling strength becomes very, very weak and remotely far away and very weak coupling, magnetization transfer efficiency is less. Obviously, if you go to 2-bond coupling, carbon proton, 3-bond coupling carbon proton, their strengths are so small. As a consequence, the magnetization transfer takes enormous amount of time. It takes more time, not very fast. During that process, what happens? Spins also start relaxing. There is a signal loss. When the spins relax, they go back to magnetization go back to z-axis. As a consequence, when they are detecting the signal in the xy plane, it is less sensitive, less signal is there. As a consequence, HMBC is less sensitive compared to HSQC because of the relaxation during long delays. HMBC usually requires twice as many scans as possible on the same sample. That means it is very, very signal averaging if you have to do, you have to acquire for more number of scans because signal and sensitivity is very, very low. And generally this is the HMBC sequence. I told you HSQC sequence, don't forget that. We have HSQC sequence is polar inept sequence, T1 period. In the T1 period you can apply 180 pulse for breaking the carbon proton coupling, reverse synapse, detect the proton and decouple the carbon. You don't forget that. That is a sequence for inept. In the HMBC sequence is a different one. Look at it. It's a simple proton carbon. Here we have a filter called long range filter, which is given a symbol delta L. This delta LR is tuned to detect correlation via small couplings. Here we deliberately have to suppress the one bond coupling. Remember, we have a long range correlation to be detected. So one bond correlation will be huge intensity. We have to subtract that. That is an important challenge here. So we have a filter which is tuned to detect long range coupling, and the rest of the thing is very simplest possible way it can be done. This is a simple sequence, and we detect the proton. As I told you, no decoupling, always observed in a coupled manner. And of course, the same thing you can do by using what is called the pulse field gradients. There is an advantage of that, pulse field gradients. Okay, so when you apply the pulse field gradients like this, remember I also told you when we wanted to subtract the carbon 12 attached proton signal or nitrogen 14 attached proton signal in the HSQC sequence, we can do two ways. One is by phase cycling, other is by field gradient. That is what I told you. Same way you can also do with the pulse field gradient, we can apply that. This is the same experiment with a pulse field gradient version of that. What is the delta LR, the long range delay that we have to use to see the correlation of the long range coupling? Remember, long range coupling NJCH is very small value. Set this delta LR equal to 1 over 2 times the long range delay, approximately 100 millisecond will be the one. For that is a small long range proton coupling to evolve about 5 hertz to 10 hertz. 100 millisecond is the long range delay, that filter delay we have to apply in the beginning of the pulse sequence. This delay is essential. Then these magnetization, the spins due to long range coupling, they will start evolving. Okay. And this during the LR period, because it is a huge value, remember 100 millisecond, what is going to happen? There are also proton-proton couplings in the molecule that will also evolve, because the strength of the proton-proton coupling is almost equal to that of the long range coupling. Long range JCH is about 8 to 10 hertz. What is the proton-proton coupling? Around 10 to 15 hertz we saw, similar magnitude. As a consequence, in the filter period LR, in the HMBC, in addition to long range CH couplings, we also have proton-proton coupling coming into the picture. As a consequence, the phase of the peak get little bit distorted. So this HMBC spectra, because of this reason, we always record in the magnitude mode. Please remember, HSQC is always recorded in the phase sensitive mode. HMBC spectra are represented in the magnitude mode. Phase information is lost. And what is this low pass filter used for? Low pass filter, it is going to pass the magnetization corresponding to long range coupling, but prevent the evolution of one bond coupling, the magnetization due to one bond coupling. So it removes one bond correlation and allows only long range correlation. And during LR, this is what happens. The multiple of long range couplings also can evolve. Remember one more thing, because if I say my LR I set for 8 hertz, if I take 80 hertz, 80 hertz is 10 times 80, 10 times 8. So as a consequence, what will happen during LR period? Multiples of long range coupling can also evolve. So that is also possible, and we have to suppress them by using low pass filter. Then this filter allow only those coupling that are smaller than the cutoff value. Anything above that, it is going to prevent. You understand? Remember, in the long filter that you are going to use in HMBC, multiples of long range couplings can also evolve. For example, long range couplings is, let us say, 8 hertz. 80 into 10, if you take 80 hertz coupling, if it is there, correlation, that also can evolve. So you have to suppress that by using low pass filter. And then that low pass filter, the advantage is it allows only those couplings that are smaller than the cutoff value set. Anything above that, it is going to be removed. And this is why HMBC sequence generally have two filters. One is a filter for the long range coupling for evolution, other one to prevent the long range evolution of this one bond couplings. So that means we have two filters. One is called a J accept filter, other J reject filter. What is that J accept? J accept is set to very small value, 8 to 10 hertz. This is what we want to detect, long range correlation. J reject is set to one bond CH coupling. This is which we want to reject, stop it. Don't allow it. See, if you know in physics, you would have understood low band pass filter and reject filter. Something will be allowed, something will be stopped. Here we have two filters. One to pass the coupling correlations coming because of long range correlations, long range couplings. One to stop the correlation coming because of directly bonded one bond proton correlation, that coupling of the order of 135. And the J reject is used to remove correlations of 1JCH. These are all called HSQC cross peaks. You know that HSQC cross peaks is because of 1JCH. That HSQC cross peaks are to be suppressed. So J reject will suppress the HSQC cross peaks, will allow only long range correlations. And this is the basic low pass filter that we use. Okay, and this is the usual sequence. And we have in between the low pass filter is put in such a way, first carbon 13 pulse creates multiple quantum coherence. That is for 1JCH only. Delta 1 is set for 1JCH, this filter. LR is for long range. Delta 1 is for one bond. So this delta 1 is set for 1JCH as a low pass filter, and what will happen, and this creates multiple quantum only for one bond CH because this is calculated for that value. And this delay is very short compared to long range. Remember delta LR when we calculated it is of the order of 100 millisecond. This is much smaller because it is a large coupling. As a consequence, in this delay, short delay, NJCH will not evolve. That is how low pass filter will filter this thing. Okay. The filter element is placed at the start of the HMBC sequence prior to the transfer of polarization onto carbon. That is the filter sequence, that is what we saw in the sequence. Then we do two experiments. One experiment with the sign of the first carbon 13 pulse plus X, other is minus X. And sign of the phase, receiver phase is always kept unchanged. This is an experiment we do. And then what we do is do the addition of both the data. When we remove that, one bond correlations are suppressed. You remember how do we do the suppression of one bond JC correlation HMBC? We have a filter here. We set the value for the filter for long range coupling and do two experiment, and with the first carbon 13 pulse here carbon 13 pulse plus X and minus X is there. First once you do plus X, second time you do minus X, and then do the two experiment, keep the receiver phase constant both the times. After both the experiment, do the co-addition of the data. When you do the co-addition of the data, one bond JCH correlations are suppressed, that will removed, and then we are going to detect only long range correlations. This is what normally is done. But of course, there are always difficulties in the experiment. When you do, there will be always some leakage, some signals won't be very good, some distortions will be there, imperfections will be there. As a consequence, there are certain difficulties, certain complications will be there in any experiment. This one can improve it. We can keep on improving the sequences so that we can get better and better correlations. One of the improved sequence is what is called a Bird sequence. Bird sequence is bilinear rotation decoupling. Bird means bilinear rotation decoupling pulse. It is alternate to low pass filter. Instead of doing a low pass filter, we can use a bird sequence. What is this bird sequence does? I will explain to you in a short way, very simple way. Bird element, this is called a bird element. Bird element, we have a proton pulse, 90 pulse, with a delay, proton 180, delay, proton 90, and then At the same time, carbon 13 channel, when the proton 180 is applied, carbon 180 is also applied. And the delay in both the cases is set to 1 by JCH. This is how the bulk element is used. But how does this bulk work? How does it do the filtering? We will see this thing. The vector picture of the bulk element will understand. For example, there are two types of carbons in any molecule. One, carbon 12 attached, for the carbon attached to proton. Other is carbon 13 attached to proton. When you put the both sample in a magnetic field, in both the cases, magnetization will be along z axis. Both carbon 12 attached to proton, carbon 13 attached to proton are along z axis. As soon as you put the sample in a magnetic field, this is what happens. Apply a 90-degree X pulse on proton. Then what happens? Proton attached to carbon 12 will come to this. Similarly, proton attached to carbon 13 also will come to 90-degree, because of 90-degree pulse come to y axis. Give a delay of 1 over JCH. Here the trick comes. What happens? This magnetization start moving by a certain angle. We know how much it moves. We know how to calculate also. Theta is equal to how much it moves, how much it precesses given by theta is equal to pi into delay into that we know, d into j, that we know that. So we apply this, and if you see that this start moving like this, it is single component vector, there is no j coupling. Carbon 12 will not couple to proton, carbon 12 spin is 0. So it is still a single, only keeps precessing, evolves on its chemical shifts. Whereas carbon 13 attached to proton is a doublet. Its antiphase doublet will be created after certain delay. Then continue further, immediately when apply a 180 pulse. The 180 pulse takes the magnetization which was here to this axis, and then continue to precess in the same direction, like here. It was going like this, it continued to precess. But whereas this antiphase remains same, that nothing will happen. And what will happen is, give another delay after 180 pulse, this carbon 12 magnetization gets refocused along y axis, completely gets refocused. There is no chemical shift evolution. Similarly, carbon 13 vector, what will happen? If you apply give a delay, these vectors start moving in the opposite direction and they refocus along minus y. See the difference. Carbon 12 magnetization, proton magnetization attached to carbon 12 will be refocused along plus y, whereas carbon 13 attached refocused along minus y. And if now we apply 90-degree pulse, this will come to minus z axis, whereas this will go to plus z axis. What is going to happen now? See, this now the advantage is effect of the bulk element, the selective inversion of the carbon 12 signal. See, carbon 12 attached proton signal is selectively inverted. Carbon 13 we did not invert, but we inverted only carbon 13, selectively attached carbon 12 proton. So, proton chemical shift evolution is refocused, heteronuclear one bond coupling evolve throughout. This is what happens. And for carbon 13 attached to proton, chemical shift will refocus, and after a total 2 delay, the doublet vector come back to z axis. By the final proton pulse, we can start detecting. Okay. And for carbon 13 spin, bulk has no effect, only carbon 12 attached proton, it gets inverted. So, with this I told you how the bulk works and everything. I am going to stop here, and we will continue with the analysis of the bulk sequence and few more HMBC spectra, everything in the next class. But this class we understood something about what HMBC pulse sequence. After completing the HSQC, why the signal intensity is very weak, everything we understood. For especially for the long range correlation, why we don't evolve, they will not be seen because of this intensity calculation. It is very small, so we don't see it. Whereas in the case of HMBC, we understood the pulse sequence is there. We suppress the one bond and detect the long range correlations. For that we have two filters, J accept and J reject. J accept will allow correlation coming back as a long range couplings, they will reject the one bond correlations. How do we reject that? There are several ways. We can do the experiment with plus x minus x phase cycling, or with the pulse field gradient experiment is also there. And also we can use different filters for doing this. One of them is a bird sequence. I explained to you what is a bird sequence. Bird will have a selective inversion for the protons attached to carbon 12, but protons attached to carbon 13, it has no effect. Then how we can use this in HMBC, how it can be utilized, we will discuss in the next class. Thank you very much.